everybody. Welcome to Hammer Down on the Market Scale Network. I'm your host, Mike Bush. Along the way, I know as we've done this show, I've talked about the fact that the USC supply chain event is one of my favorite events. And there's several reasons for that. The first one is quite simply, it's a room full of kids who are really excited. It's a master's program dedicated to folks that want to get into supply chain. And to be totally transparent, that show is the reason that that Hammer Down exists, right? Like I sat in a room, had a bunch of people with questions, bunch of people with interest, and I thought this is so cool. But beyond that, the presenters there and the folks that are alumni to USC and the folks that come back to chat are some of the most forward thinking, interesting people in supply chain. And my next guest fits that bill. We met at the USC supply chain event, and I realized quickly two things. One, this woman's brilliant and knows so much more than I do that it's crazy. And number two, she's super patient because she was willing to sit there and answer all my questions. She's Michelle Lampa. Michelle, welcome to Hammer Down.
Thank you so much, Mike, and I'm really excited to be here.
Oh, so Michelle, you're in business development for Pasqal. Let's get right into it. What does Pasqal do? What are the problems you're out there solving?
Sure. So Pascal is a full stack quantum computing company based out of France. And quantum is all the rage right now. I mean, even my mother-in-law ended up telling me that she saw the 60 Minutes slot in which they started talking about quantum computing. So I guess quantum has started becoming mainstream, and it's very exciting. What people don't realize is there are 9 different qubit modalities, which means that there are 9 different approaches to quantum computing, which means we're not there yet. Ours is in the neutral atom approach. And so that's what Pascal does. And Pascal is one of those companies that is, it's full stack. And so we do everything from offering and manufacturing, delivering and integrating our HPCs, which are QPUs, quantum processing units. 3 of them have actually been integrated to HPCs already, so high performance computing centers around the world. But we've also sold to the largest oil and gas company in the world as well, which means that in a way we are also delivering enterprise level devices as well as cloud access to our devices, as well as working with end users, those in oil and gas, those in energy, those in life sciences, and basically trying to translate their complex data sets to quantum to make it more optimized and the approach for outcomes.
Okay, let's take a quick step back. What is quantum computing? And how is it different from the other buzzword we hear in supply chain, which is AI or machine learning?
Exactly. So, I mean, it's just a different way of approaching computation, right? So if you think about the machines that we have right now, the laptops that we're on right now, our phones, basically it's very much on like, if this then that, if this then that, right? And that's how most of it happens. For quantum computing, it's more on also on the kind of probability side. So in the end, say you have a maze and you have, a mouse that's trying to get to the end. In classical computation or even classical devices that we have, you would have that mouse go in, and then as soon as he makes a wrong turn, it's like, all right, we got to run this again. And that mouse will learn not to go down that route. That takes a lot of time. Right. And so for quantum, on the other hand, it's a way that it's a spooky feature of entanglement in which various different qubits basically have the same maze and have a mouse go in completely different ways, and they get to the same outcome much faster. Right. So you can see how if it's done all at the same time versus waiting for, oh, he made a mistake, like we got to run it again. And that's the differences. Also, the difference is because quantum in itself is the manipulation of atomic and subatomic particles. So think back to like 7th grade science class, right? And
Okay.
you're thinking of like protons, neutrons, electrons. Those are the materials, those are the aspects, attributes, the little pieces that we're actually working with and manipulating, which means that it's very hard, right? And so, at least for us, for example, we use lasers. So going back to even that 60-minute presentation on quantum where IBM is showcased, they have this gigantic chandelier, and it requires their qubits to be colder than deep space in order for them to work, for them to actually apply certain algorithms and apply anything on it. But for ours, we don't need that. Ours is actually room temperature. And as our CEO likes to joke, it's equivalent to running 5 hairdryers. So you can run 5 hairdryers in room temperature, or basically get it to, or basically run a quantum computing device. And so hopefully that gives you an idea of what the differences are between classical computing versus quantum. Also, I guess one of the things that makes it different is because I showed you or told you about that aspect of like if this and that, that's fine for even like 1 + 1 = 2 or 2 + 2 = 4, or if we do this then we can do that. AI and ML works well in that, except AI and ML and what we're seeing today uh, has actually accelerated and exposed the limitations on what can be done on classical hardware because it's taking way too long, right? Like the data sets that we're seeing are getting way more complex. We're already hearing it even in the supply chain industry and logistics industry, right? I think I've listened to a couple of your other episodes, and some of them have gone into, all right, it's okay to do plan certain routes just based on Google Sheets because it's 1 or 2 routes, but go beyond 2 routes and all of a sudden you need a lot more than that. It's fine for like 3 routes, 4 routes, 5 routes, but then you start adding in shipping routes, LTL, you go into, ocean freight, and then you also go to air transport and also add on the complexities of certain, borders and what goods you actually have and how that's going to be moved. And then that becomes a really complex data set. It is no longer just like, if Betty wants to sell bread to the next town, like let's see, it's like, no, actually we have to take into account where are the ingredients coming from. Is there certain areas that can't be delivering that, and can we optimize even pricing? That becomes a complex data set that essentially gets compounded on AI, ML, and classical hardware, where eventually you end up seeing that same processing power will actually take a really long time. So for quantum, very similar to that maze thing, is there a way that we can just line it up, flip a switch, and basically get it done in microseconds? That saves time, that saves processing power, and that saves energy, which we're already seeing. AI and ML is taking up huge amount of energy. Even Microsoft, I think they just bought an island just in order to handle the energy costs and energy needs that AI and ML requires at this point.
Right. So now, if bear with me if this is wrong. If I understand it entirely, it used to be you'd have something on your laptop. There's two types of stuff on your laptop. There's there's the memory, which is the database, and then there's the RAM, which is pulling in for or the memory. I'm sorry. So there's database, but memory, and then memory goes in and pulls the information you need. And that's how computing has historically been done. We've gotten to a point where we said, well, what if we just store everything in memory? And that's in memory computing, and that's a way to get faster. And then quantum is taking that next step to say, forget about that. Let's make it everything's available in real time. And instead of saying we want to access one piece of information or a few pieces of information, quantum is we want to access the whole darn thing. Is that accurate so far? Or where am I wrong?
So where it gets kind of tricky is like very similar to the quantum is not going to do the 1 + 1 = 2 type of situation. And right now we're not seeing like quantum is one of those where it's just specifically for complex data sets, right? And so it wouldn't be just like taking all that memory and then just like dumping it into this thing. What we're trying to do is basically trying to even optimize certain algorithms that would be for complex data sets. So for the traveling salesman problem, for example, or a salesperson problem. Essentially, that's one of those that would be very much a quantum problem that we would like to address. It's an optimization problem that would take on major processing power. For the memory and the RAM that you were talking about, it's one of those where what could be a quantum problem is essentially more on the understanding the various different aspects on, are there better ways that we can optimize even data input, or even optimizing that whole process on how do we process data even faster than we do today. One of the things that makes quantum computing very different is the fact that it also takes into account the quantum properties that don't necessarily can be done, right? And it's because classical is very much like if this then that, whereas quantum, like even for the laws of physics, what would generally be we see like what comes up, what must come down, that exists especially for bigger objects. But when it comes down to quantum, we were talking about protons, neutrons, electrons, and stuff. They may or may not actually follow the same laws that we are accustomed to. So it's a completely separate approach. And so it's not necessarily replacing what currently exists on classical hardware. It's a completely different approach for complex data sets. And like I said, like, quantum has basically, or AI and ML has already exposed the ceiling of what can be done in classical hardware. For quantum computing, on the other hand, because it kind of like extends like what can be done on the computation side, people automatically assume this is a quantum problem. But one of the side effects of going down, like, let's turn this in quantum, is we've actually begun identifying various different algorithms that still extend what can be done on classical. So we're actually improving what can still be done on classical hardware. Hopefully that,
No, that
helps.
was great. That was great. So
Okay.
basically, it's in addition to solving more complex problems than have historically been capable of being solved, you're also saying how can we optimize the tools that already exist, which is kind of
Yes,
great, right?
exactly.
So how on earth did you get here to be in a position where you're talking about quantum computing in supply chain? What is your background? What turn did you take? Because I'm fascinated by this.
Yeah, no, it's actually really funny. So it's a lot of people actually ask me like, "Oh, did you go into quantum or are you a physicist?" I'm not, and this is actually what's needed, especially in in the future of quantum or emerging technologies. We need more diversity and in it. And I'm not talking about just like, race or gender. We're talking about, you know, um diversity and experiences, right? Because quantum computing is a tool. And the engineers, the scientists that are on this, they're fantastic at what they do. But understanding it's, as someone, so I actually started in international relations and international business. I worked for the state of Massachusetts or the Commonwealth of Massachusetts. I also worked for the Massport, so the Massachusetts Port Authority. So I worked really closely with everyone on the shipping side, especially at the Port of Boston, as well as Boston Logan Airport and Worcester Regional Airport. And the whole point there was it was really fascinating to be exposed to all the different moving pieces that were exposed that work in supply chain and logistics and just moving goods from point A to point Z. But one thing that I was really interested in was like, how do I get into technology? I don't like being that person that's just like, I don't know how to do this or I don't know how this works, could you show me? Instead, I was like, wait, how does, like it's a curious mind in which I kept asking, but why? But why? And after a while, I was actually doing really well in my world of and my career in international business. And I literally put a hold on my career to learn how to learn and become a full stack web developer. So in a way, software engineering. I realized I didn't really want to be a software engineer and I went into product management at Wayfair.
Sure.
And that was really fascinating because, you start doing the on-time metrics reports for all the goods that are being shipped on all the large parcel orders, the small parcel orders, and understanding if we're going to launch a new warehouse for, and various different pull points, does that help or does that not help? And it was really fascinating to see we can build all the tools that we want. for truckers to like check in, to help them with their optimization of routes. But in the end, they are the users, and you may think you are building the most amazing tool ever, but they will always find a reason to break it, right? And it's the same with every single product. It's not just drivers, it's not just, we do the exact same thing. You give me a hammer, I will find a way to break that hammer, right? And it's because like it's supposed to be used for nails, and in the end, like, I'm gonna mess with it. And for that reason, like I ended up being like, I just kept pushing like, why? And I went back to government, and I was the vice consul for technology at the British consulate. And I attended this quantum conference in Boston. And I started talking to someone that was in lasers. It turns out he was a co-founder CEO, and started off, how do we help you on behalf of the consulate of the UK? And then eventually started to sound like a, job interview. And then that, exposed me to the world of quantum computing, quantum, not just quantum computing, quantum. So we're talking about the manipulation of atomic and subatomic particles in order to not just do computation, which is basically, the zeros and ones in which, you excite like certain types of atoms, and the way they do it, it's going to be exact every single time. That's how you apply your true or false values. The same applies for even how they do atomic clocks, for example. So telling time, how we tell, what we believe is telling time is like looking at like, our watches or whatever, but actually there's a lot more to that. The laser company that I was working with created like like lasers for atomic clocks, for gravimeters, accelerometers, literally, because atoms are the smallest things in the universe. You could drop it in a electromagnetic vacuum chamber, and it would be able to tell you everything that's beneath the surface of even the structure you're in, because it'll find its way down, and it'll bring back all this information about even down to like a 1970s Coke can that was just kind of accidentally left in the structure. How is this helpful? It helps insurance companies, for example, if they wanted to see if a structure was at risk of sinkholes for, insurance protection, or, even for defense modules, if they wanted to enter certain world, like places underneath the surface in the water. GPS doesn't touch that. And so like you would be able to use accelerometers in order to actually identify, you know, uh, what is underneath the water, just by using that same approach and understanding the electromagnetism and the electromagnetic fields that actually exist underneath the surface in the water, which helps in navigation. And so there's certain various different aspects that can still be used and explored. And that's what I got exposed to. I read Richard, at the time, I didn't even know his name was pronounced Richard Feynman. I said Richard Feynman, and I read Quantum Electrodynamics just for fun, I guess. And I ended up realizing object-oriented programming, for anyone that's in like the software engineering world, for who think quantum is just like outside, it's the same thing. You're building atoms on top of atoms, you're building objects on top of objects. And quantum electrodynamics is basically understanding the wave particle dualities in which light can be used as both an object to move things, as well as also like affect change in other ways too, or be the thing that does other things. So anyways, so
Yeah,
that's
awesome,
how we got
awesome.
into it.
So, if I were to ask you to make maybe one or two predictions, what are current supply chain problems that are going to be solved by quantum?
Sure. I mean, supply chain problems that could be solved by problem. It's obviously, it's not obvious, but like I would say optimization problems, right? Like there's always going to be the human problems that exist, but there are other things that can be forecasted. For example, like for insurance measures, right? Like there's ways to understand well, besides like, freak accidents, like, or freaks of nature, like, what's happening in California right now. People can see like, okay, based on NOAA's, data sets that they've taken from all the various different storms and hurricanes that have happened, as well as all the other travesties that have taken place around the world, can we forecast, potential routes that would be better suited for getting this to the goods from point A to point B? Like, that is one thing that could be very much used on quantum. I can see that happening. Another thing for supply chain is basically route optimization that we talked about. But beyond that is it's like those type of complex data sets. But another thing that we kind of talked about when we were at the supply chain summit was essentially like the introduction to new technologies that are going to be introduced via quantum, right? So better batteries, and that could be help with what we were talking about. Like, if we're trying to lower and decrease the carbon footprint, how are we going to do that if we don't have good enough batteries to actually get the types of trucks that we want out and going, right? We've also seen like certain batteries explode. Like, what does that actually mean? There are certain quantum properties that exist for materials discovery and new batteries discovery that can actually affect the full on supply chain industry. That's something that's really interesting that I think will actually make a major impact as well as also like just aerodynamics, better design features of certain, transportation vehicles in general, right? And I think those are all very much going to change the way supply chain is and how it's perceived.
Okay, that's three amazing use cases. So Michelle, you're based in Boston, right? And if I've got to ask you the question when it comes right down to it, last time I was in Boston, there were an awful lot of highways closed. There was a lot of street closures, a lot of traffic. I think it took me like 3 hours to get from Logan Airport to Fenway Park. Was not impressed. If I'm thinking of it from the Boston centric perspective, is quantum solving the traffic issue for me?
It can, because one of the things that Boston actually has is a really great public transportation system as well, right? And one of the things that we're trying to do is try to avoid all the Storroad getting all the trucks getting Storroad, right? And on Storroad Drive, apparently it's a running joke in Boston, like trying to see how many trucks and moving trucks get stuck on Storroad Drive because somehow everyone is moving in and there's always bound to be one person that drives that U-Haul and destroys everything. But better the transportation system, even though we have it set in place, the T isn't the greatest, right? But there are ways that we could potentially do better discovery of better designs for trains and how to make it more optimized, as well as get a better way to just manage the traffic, right? We had the big dig and there has to be better ways and hopefully never or hopefully not doing what New York is doing with the surge pricing for traveling through at certain peak times. I don't think people should be, penalized for having to just get goods from point A to point Z, right? And they're just doing their jobs and you shouldn't be financially at least penalized for that. So I think there are better ways and I think quantum can do that and we'd love to be a part of that. And like I said, like we are HQ'd in France, but one of the things that we are doing, we are advancing our operations. We are in advanced conversations right now and expanding our US operations, and we very much like to get to know you and what your needs are, at least in the United States.
Getting Storroad is now my new favorite phrase.
I
Like
know,
this.
right? You should
Hey,
Google
yeah,
it.
I got Storroad. I was stuck in traffic. I love everything about that. So Michelle, everything you've said makes sense and is incredibly cool and forward thinking, but I have to assume when it comes to costs, they're through the roof, right? Like a small business or a mid-sized organization, probably not jumping into quantum quite yet. Am I wrong?
Yeah, no, you know what? You bring up a really great point because there are companies that, the gigantic companies, they can probably, afford to put some money towards R&D, towards, identifying and testing out new emerging technologies like quantum. But what's really great, and I have to give a shout out to at least the government that are the governmental entities around the world that are investing, because in the end, they're actually trying to get utility scale of these emerging technologies. And by doing so, they're actually providing all these major grants in order to help companies offset costs in pursuing more of these emerging technologies. And I think it would be great for companies like, for example, ARPA-E, the energy focus. They have various different programs on even battery discovery, new materials discovery, and even route optimization. Opportunities. And I think those are some of the programs that maybe some companies on the smaller scale aren't even aware of. And I'd very much encourage you all to kind of look at it and look into it a little bit more. Another one is the ARPA-I one. So it's based on infrastructure with the Department of Transportation. And they're very much focused on, route optimization as well. And basically, how do we improve the overall infrastructure and supply chain that is currently existing? And I very much think that that is something that at least we in Pascal would love to work closer with various different companies that want access to our technology and see whether or not this can actually, enable and the advancement of whatever you are trying to do and provide to your customers.
Sure, absolutely. And now, correct me if I'm wrong. When you talked about ARPA, isn't ARPA the actual organization that kind of inadvertently or by design created the internet?
Yes,
Okay, gotcha.
absolutely. And so, it's really cool to be a part of that and to see the various different use cases. So you could do materials discovery, but also do other things. And you would be a part of this whole fantastic journey of this new technology. I don't think anyone back in the day actually thought that, the first computer was going to be, I think they just thought there was going to be like, oh, we can solve major mathematical problems. I don't think they at all thought about the fact that some of the major use cases was watching cat videos on YouTube.
I'm not sure that they still should be the major use cases, but you're absolutely right. I try to end every show with the same question, and I think I know your answer a little bit, but would love your feedback here. So at an event like the USC Supply Chain Summit, or wherever it happens to be, Fenway Park because you're in Boston, and Fenway is a wonderful place. You run into some newer recent college grad who says, or soon to be college grad who says, "I'm thinking about going into supply chain." What's the piece of advice you give that kid?
Sure. So there's one thing that I've heard from having so many conversations, especially with various different universities and colleges around the world. One of the things that they are focusing in on, and I think is really important, is to become more data aware. Right. Supply chain, we all know that every single good, we are affected by all of it. And we are no longer just an ecosystem or even an environment or just a people that believes in just having one or two things. We want it now. We don't want it like tomorrow. We don't want to wait. We want it now. But in the end, it's like data, right? And so being part of supply chain, it was really fascinating to me because of the fact that I didn't know much about it. I thought it was really like, I thought it was just like, oh, well, that's just, planes and like trucks, moving things around. But it's so much more complex than that. It's very much solving problems. But one of the things that I think the next generation is going to be very much aware of and need is to become more data aware. Whatever you do, whatever you are going to be touching and whatever you are going to be playing around with, it's all going to be data heavy. And that means like even knowing that if you are going to like open up a website, it could be malicious. They could get access to your company's like, I don't know, anything, and they could shut down that whole supply chain for various different companies. That one mistake actually affects so many different companies. I remember the Petya non-Petya attack that affected even Mars company. I didn't know that Mars actually also created foods for dog medicine or pet medicine, and so they actually had to make a huge decision while they were trying to get their cyber thing and supply chain fixed. Like they had to give all their information for like and basically tell their customers, please go to these competitors because we care about your pets and we don't want you being affected by this. And so that's something that's really important and something that I thought was really fascinating. And when I was at Wayfair, I remember one of my colleagues at one point I was like, "Oh my gosh, this isn't working." He's like, "You know what? One thing you need to remember, we're in furniture. We're not like affecting lives, right?" And I was like, "That's fascinating. And yes, technically we're in e-commerce and it's furniture, but supply chain affects various different industries. And so that same approach can't be just, you know, affected to just like or appreciated for just e-commerce. It also means a Johnson and Johnson or a life sciences company who or biopharmaceutical company that needs to get this life-saving drug out to market. If we're not more data aware, if we're not more, appreciative of every action we do actually affects the overall supply chain, like ecosystem, then I think anything could happen. And it could not be in the best interest of everyone involved.
Understood. So, Michelle, if somebody wants to learn more about Pascal, if somebody wants to get in touch with you, what's the best way to do so?
Sure. It's michelle.lampa@pascal.com, or you can check out our website at www.pascal.com. That's PSQAL, because everything in quantum starts with a Q or has a Q in it. And you can also find me on LinkedIn. I'd love to have more conversations about what quantum means. I would love to talk more about like my journey as well as, how you can start looking at quantum and how we can expose and provide more access.
She's Michelle Lampa. I'm Mike Bush. Thanks for listening, everybody.
Thank you.